When you look at a giant aircraft carrier like the USS Gerald R. one question instantly hits you. How can something this huge not flip over? From the front, the hull rises from the sea like an upside-down pyramid. Then you notice the flight deck. It has massive side platforms packed with heavy jets. Each aircraft weighs tens of tons. The ship itself weighs around 100,000 tons. It looks like a floating skyscraper. So why doesn't it topple? Is the crew just living one mistake away from disaster? To understand that, we first need to answer a simpler question. Why doesn't an aircraft carrier sink? If you throw a hammer into the sea, it drops straight to the bottom. But a rubber ball floats up like a cork. The reason is buoyancy, also known as Archimedes force. A floating object pushes water aside. That displaced water has weight, and the water pushes back upward with the same force. So, the secret is simple. If the average density of the object is lower than water, it floats. A steel aircraft carrier sounds like it should sink, but it does not behave like solid steel. It contains enormous empty space inside. When you count the total volume, including all the internal compartments, the average density becomes surprisingly low. Let's use rough numbers. The carrier's total volume up to the deck is about 1.3 million cubic meters. The maximum loaded mass of the Gerald R. including fuel, crew, and aircraft, is around 112 million kilograms. Divide mass by volume, and the average density is about 86 kilograms per cubic meter. That is far lower than water. It is even much lower than many types of wood, which can be around 550 kilograms per cubic meter. In simple terms, the carrier is like a giant hollow box. That's why it floats so high. But floating is not the same as staying upright. The harder part is stability. A ship can float and still capsize. This is where the idea of the center of buoyancy and the center of gravity matters. Buoyancy acts upward through a point called the center of buoyancy. Gravity acts downward through the center of gravity. When the ship is perfectly upright, these forces align. But when the ship tilts, the underwater shape changes. The center of buoyancy shifts sideways. That creates a restoring force. Engineers use a key concept called the Metacenter. Imagine a line straight upward from the shifted buoyancy force. Where that line crosses the ship's center line is called the Metacenter. If the ship's center of gravity is below that point, the ship returns upright. If the center of gravity is above it, the ship becomes unstable and may flip. The bigger the distance between the metacenter and center of gravity, the more stable the ship is. Now here's the scary part. Aircraft carriers are not simple ships. Their weight changes constantly. They have many aircraft. They lift jets from hangars to the flight deck using elevators. They launch jets. They land jets. They move planes across the deck. They also burn huge amounts of aviation fuel, which is stored low in the ship for protection. As fuel is consumed, the center of gravity can rise. That reduces stability. So balance is always shifting. And aircraft carriers still must operate in extreme situations, not only calm sea conditions. That is why U.S. Navy carriers face brutal tests before full service. One of the most famous tests is shock trials. This simulates what happens if the ship faces underwater explosions, like mines or torpedoes. During these tests, the Navy detonates massive charges near the carrier to create violent shock waves. The Gerald R. went through this in 2021. Charges as large as 40,000 pounds, about 18 tons, were exploded near the ship. The goal was to see if the hull, systems, and structure could survive strong impacts without breaking. The Ford passed. This was the first carrier shock trial of this scale in decades. Another major test is high-speed maneuvering. Even though carriers are enormous, they still need to turn quickly. If a carrier detects a torpedo threat, it cannot just sail straight. It must change course fast. During maneuvers, a ship this heavy can tilt strongly. A full-speed turn at around 30 knots can create large roll angles and huge internal forces. The flight deck can tilt dramatically, making it easy to imagine planes sliding off if not secured. So how do designers make this giant ship stable? First, hull shape matters. Carriers are built with a wide beam and carefully designed underwater geometry. This lowers the center of gravity and raises the effective buoyancy point. One special feature is the bow bulb under the waterline. Many people think it only reduces drag, but it also helps with stability by shaping water flow and supporting balance. Second, carriers use ballast systems. Ballast tanks hold seawater. By pumping water in and out of tanks on different sides, the ship can shift weight and maintain balance. When aircraft move or fuel levels change, ballast can compensate. Pumps can move thousands of liters per minute. In normal operations, this can be controlled automatically. In unusual situations, operators take manual control. Third, modern carriers use active stabilizers. These are movable fins or blades that adjust to waves. They reduce rolling motion in heavy seas. Sensors like gyroscopes detect ship movement. Computers calculate the best angle for the stabilizers. This makes flight operations safer, even when the ocean is rough. Still, no system is perfect. History shows even aircraft carriers can be damaged by severe storms. In past decades, U.S. carriers like USS Bennington and USS Enterprise experienced extreme storms that damaged deck aircraft and equipment. Some aircraft were washed into the sea. The ocean does not care how advanced your ship is, but even if a carrier survives the ocean, war is a different threat. For many years, U.S. aircraft carriers were seen as nearly untouchable. During the Cold War, it was believed that the Soviet Union would need a massive strike package of dozens of bombers firing heavy anti-ship missiles to seriously disable a carrier. The losses could be extreme. It was almost a suicide mission. Today, hypersonic weapons are changing that calculation. New missiles may travel faster, maneuver harder, and reduce reaction time. That makes carrier defense more difficult. So the U.S. relies on layered defense. A carrier does not sail alone. It travels with escort ships equipped with the Aegis combat system, capable of tracking and intercepting threats at long range. At closer range, systems like CIWS rapid-fire guns can shoot incoming missiles. Fighters like the Super Hornet can also intercept threats. Electronic warfare adds another layer by jamming radar and confusing guidance systems. But what if missiles still hit? Then the carrier's last hope is compartmentalization. The ship is divided into many watertight compartments separated by strong bulkheads. If one compartment floods, it can be sealed quickly. That prevents water from spreading and keeps the ship afloat and stable. The exact number of compartments on Gerald R. Ford is classified, but carriers of similar design can have hundreds of watertight sections across all decks. Critical areas below the waterline are heavily protected. This system can save the ship, but it is ruthless. If people are trapped in a sealed compartment, the priority is the ship's survival. This has happened in naval history, where automatic sealing cut off trapped sailors, and even compartments are not a magic shield. If a hull breach floods several compartments at once, stability can be lost. A real example is Norway's frigate Helge Ingstad, which capsized after flooding spread below the waterline. So, could an aircraft carrier ever capsize? Yes, in theory. But in reality, it takes extreme damage. Remember, the carrier's average density is far lower than water. To truly sink or flip such a floating hollow city, you must overwhelm its buoyancy and stability at the same time. That usually requires catastrophic damage, often on the level of multiple heavy strikes or nuclear-level destruction. So, the short answer is this: the Gerald R. Ford does not topple because it is designed not to. Its shape, ballast systems, stabilizers, and compartment structure constantly fight gravity, waves, and combat shocks. Unless the carrier faces a truly overwhelming strike, it is far more stable than it looks.